All right, guys, so we are going to power through a whole bunch of review problems, starting with we've got just a bunch of derivatives, mostly chain rule stuff. Kind of really covers all of our derivative rules that we've seen, not only in the first half of the chapter, but the second half, which is what we're actually testing on. So starting with number 35, we've got y equals, so this one, we did a bunch of these review problems before the first half of chapter 3, and then we stopped. There weren't very many we were able to do because most of them require the chain rule, starting with this one, which we didn't do until this chapter. So here is our original function. The main function is some quantity raised to the sixth. So what we do is we take the derivative with the 6, throw the 6 out front, drop the power down to 5. So remember what happens is we've got a nested function. We can always call the nested function u and do a u substitution. The nested function does not go anywhere. I cannot emphasize that enough. So power comes out front, new power is 6 minus 1, and then what I do after that is I multiply by the derivative of the nested function. So the derivative of this quantity right here, always make sure you've got that in parentheses. Derivative of x to the fourth is a 4x cubed, and then minus the derivative of 9x is 9. So keep in mind, I've said to you guys, simplify to your level of comfort. I would say to take the 6 times this stuff, so you could have 24x cubed minus 54, and then times this quantity to the fifth. And there's not much more you could do with that anyways. So that would be your final answer for that one. Next one on the list is 39. Okay, so this one is a chain rule inside of a quotient rule. So that's why I've been advising, very strongly advising, that you guys kind of keep yourself organized with the high and low. So the numerator is z. Low is the square root, which I'm going to write as 1 minus z to the 1/2 power. Always keep in mind that the radical functions, the rational functions, are really just power rules. So always write the power. It'll help you. And then d high, the derivative of z is just 1, because z is a linear function. For d low, we've got a little chain rule here. Power rule starts us off, the 1/2 comes out front, and then the power drops down by 1. The nested function stays in place, and then I multiply by the derivative of my nested function. So the derivative of this function here, it's linear, and its derivative is just a -1. Okay, so we've got all our pieces set up here. So we start with low d high. So just a 1 minus z to the 1/2, and then times 1, which I don't need to write, and then minus high d low. So I have z, I guess I could throw like the 1/2. So the -1 will make this positive. Could throw a 1/2 out front, and then the z, and then the 1 minus z to the -1/2. Okay, and then all of that over, low, low. So when I take that denominator and I square it, I just end up with the quantity 1 minus z, because it was a square root, so when I square it, I just get 1 minus z. Let's kind of separate some things here. There we go. And there is a lot you could do to continue simplifying that, but it gets to the point where the algebra just really isn't worth our time. So I would leave it like that. You'd get full points from me, you'd get full points from the AP test. Got a little multiple chain rule here. Okay, so let's start by doing a u substitution. Okay, so this thing, the original inside function, kind of like the innermost function here, we're going to call that u. So u equals x plus the square root of x plus the square root of x. Okay, so that's our innermost function, which means I can write y as the square root of u, which is u to the 1/2. Okay, so let's start with our derivative. So y prime, I do a little power rule here, 1/2 comes out front, my power drops down to a -1/2, but because u is not an x, that means it's a nested function, so I have to multiply by the derivative of u. So this is all fine and well, this will eventually be my final answer. I know what u is, it's right here. I do not know what u prime is. Alright, so I am going to do another substitution. So here's kind of an inside function. Yeah, probably should. No, you know what? We're just going to go for it. Everybody's fine. Okay, so start with the derivative. The derivative of x is 1, and then plus, the one thing I am going to do here is write these as powers. Powers will make everything, so that should be an x. Powers will make everything just a little bit easier. Okay, so this square root right here, I wrote it as quantity 1/2 power, and then this square root, I wrote this as x to the 1/2, and this should be an x. I'm sorry about that. So here's our function u. So when we take the derivative of x is 1 plus, and then for this piece right here, we do another chain rule. 1/2 comes out front, leave the nested function exactly where it is, power drops down to a negative 1/2, and then we multiply by the derivative of the nested function. Okay, so the derivative of this piece right here. So the derivative of x is 1 plus the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And that's it. All right, so now keep in mind this whole quantity is all multiplied together. That is the derivative of this piece right here. Don't forget that we have the 1 there, which is the derivative of x. Okay, so now let's plug all this stuff in. So 1/2, now plug the u back in here. Okay, and then times u prime, that is this whole thing right here. Make sure we've got it in parentheses. Okay, so close that and close that. There we go. This is just a nightmare to even think about simplifying, so I would just leave it just like that, y prime. There's some things, I mean, like 35, multiplying these two expressions together to simplify is one thing. Attempting to simplify this thing, totally different ballgame. So we're just going to leave 43 just the way it is and move on. Okay, 47. Y equals the sine of 2x and then times cosine squared of x. Remember, cosine squared is really that. Okay, so we're going to do a product rule because we have one function and then a second function. Both of those functions require chain rules. So let's do a little work over the side. So u equals the sine of 2x, v equals cosine of x, quantity squared. So u prime is the derivative of this thing right here. It requires a little bit of a chain rule. It's kind of a little mini guy. Outside function is sine. The derivative of sine is cosine. I leave my nested function in place. And then, here, let's keep these on here. And then I multiply by the derivative of my nested function. And the derivative of 2x is 2. Okay, and then v prime equals this one, the main function, is a power rule. So what happens is the 2 comes out front. Technically my power drops down to a 1. And then I multiply by the derivative of my nested function. So the derivative of cosine is negative sine. Okay, and I threw the negative out front in case you're wondering where that went. So now I've got my pieces. I am going to do a little product rule. So cross multiply and add. So these two get multiplied together. So I'm going to put the negative 2 out front. Sine of 2x, cosine of x, sine of x. It's a beautiful term here. And then plus, then I multiply these two together. I have 2 times the cosine of 2x times cosine squared. Okay, so that would be my derivative. Again, I wouldn't even dream of simplifying any further. 51, y equals 8 over 1 plus the cotangent of theta. This one's actually not bad. This is just kind of your run-of-the-mill quotient rule. There's no chain rule required even. So high is 8, low is 1 plus cotangent of theta. D high, the derivative of 8, since 8 is a constant, the derivative is just 0. That'll make things pleasant. And then D low, the derivative of this term right here, the derivative of 1 is just 0. The derivative of cotangent is negative cosecant squared. Okay, so quotient rule. Y prime equals low D high, that is just 0. And then minus high D low, so minus a negative, we have plus 8 times cosecant squared of theta, and then all over low, low. Okay, so just, you can leave the 0 or pretend it's not there. This guy right here would be our final answer. 55. F of x equals 9 e to the negative 4x. So we've got a little bit of a constant multiple rule there with the 9. So remember, when you're taking derivatives and there's a constant out front, you just kind of leave the constant out front. And then here's the part I need to take the derivative of. So my main function is e to the x, or like e to the u, I guess we could say. So when we take the derivative of e to the u is just e to the u. Remember, we always leave our nested function in place, and the last thing to do is multiply by the correction factor. That's the derivative of negative 4x. Since it's linear, the derivative is negative 4. And so this is what I'm talking about when I'm saying some things are really easy to clean up. This is very, very easy to clean up. All I need to do is multiply the constants. That is something that I would really expect you to do. Cleaning up something like number 43 is not. Okay, 59. Okay, f prime of x here, the main function is natural log. The derivative of natural log is 1 over the nested function, 1 over x. Or in this case, it's 1 over 4x squared plus 1, because I always leave my nested function in place. And then I multiply by the derivative of my nested function. So the derivative of this expression right here is an 8x. Again, when we're talking about cleaning up, this is one very, very easy thing that you can do, is just to rewrite it like this. This looks so much cleaner than this does. Okay, 63 f of theta this time equals the natural log of sine theta. We may have done this in the notes. This looks really familiar. So when we're taking the derivative of natural log of u is 1 over u to start, so 1 over sine of theta. But then because a chain rule is required, because I've got a nested function, I then have to multiply by the derivative of the nested function. And the derivative of sine is cosine. So this is really cosine over sine, and if we know our trig properties, cosine over sine is cotangent. So that would be your final answer there. 67, we're nearing the end here of all of our derivative rules. 7 to the negative 2x. These ones, for some reason, we're having a lot of trouble with these exponential ones. So f prime of x, the main function is 7 to a power. That derivative starts with the coefficient of natural log of 7, and then times 7 to the power, but then times the derivative of the nested function. The nested function is a negative 2x, its derivative is a negative 2. So let's clean up. Our coefficient can be a negative 2 times the natural log of 7, and then times 7 to the negative 2x. All right, so we can write it out like that. So flip for our next one. We're on to 71 now. Okay, so now we've got a little inverse trig mixed in here too. So f prime, again, this is now the third one in a row with natural log. For natural log, the derivative is 1 over u, whatever the nested function is. So 1 over cosecant inverse, but then I multiply by the derivative of my nested function. So let's kind of walk through, and this is what I'd like you to do while you're doing these inverse trig, because I gave you a lot of tricks to help you remember. First of all, so now we're working on this derivative here. All of the co-functions have negative derivatives, so I know that. So now I know that now it's based on the secant derivative. So sine and secant have square roots and subtraction. And secant has the absolute value of x because secant sucks. So that is your derivative there. We could combine everything up into one fraction if you wanted, but that's really the only cleanup that I would recommend. So something like that. And you really wouldn't even need to do that if you didn't want to. All right, 75, the last for this section. We've got g of t equals sine squared of t, is that right, raised to the t. All right, so this one is a little bit sneaky. We've seen some problems like this. Anytime that we have like a t as a power like this, and a t as a base, so we have a variable base and a variable power. This is where we brought out the logarithmic differentiation. So let me clean something up first of all, because remember, sine squared is really like this, but then I'm raising the whole thing to the t. So what I can actually write is this is sine of t raised to the power of 2t. So this one, I've got, like I said, a variable in the base, a variable in the exponent. This one I break out the logarithmic differentiation. So let's pretend, just for a moment, that this is a y. Okay, so we start by taking the natural log of both sides. So the left just stays natural log of y. The right, we apply this property that says the power can come out front as a coefficient. Okay, and then I take the derivative of both sides. This time it will be with respect to t, because that is my independent variable over here. Still going to have some implicit differentiation involved. So the natural log of y with respect to t is 1 over y times dy by dt, and then equals, over here I'm going to do a product rule. So I have u here, and then I have v here. So I do u times v prime, and for v prime I'm going to need a little bit of a chain rule. So I have 1 over sine of t, that's the derivative rule, and then times the derivative of sine, which is cosine, and then plus v, which is the natural log of sine of t, times u prime. The derivative of 2t is just 2. So let's clean this right-hand side up a little bit. So the 2t will stay. Cosine over sine, remember, is cotangent. So lots of t's here. And then plus 2 times the natural log of sine t. So last thing that we are going to do from this spot right here is we're going to multiply both sides by y to get the dy by dt by itself. Remember though, when we did these in the notes, instead of y, you want to put down the actual function. There we go. Isn't it beautiful? Okay, next one that we've got is number 83. This is one of the inverse derivatives. So f of x, and it gives the function up above, f of x is equal to x times e to the negative x. So showing that a function has an inverse, really the only thing that you can do for that is just kind of graph it. And I won't ask you to show these things, but just to show you what they're looking for. So I'm going to graph this. So x and then times e to the negative x. So we're supposed to be showing that it has an inverse on the range from 1 to infinity. So here's this part right here. Goes on 1 to infinity. Keep in mind that all of the x values and y values swap. So if we were to flip this over the line y equals x, what would happen is we would get something that's not a function. But if we look from just this piece on, that piece would be flipped over and that piece would have an inverse. What we need to do, because you know how functions, you have to pass the vertical line test. If you want to see if something has an inverse, you have to see if it passes the horizontal line test. In functions, each y can go to only, or I'm sorry, each y can come from, no, each x can go to only one y. Each x can go to only one y if it's a function. So if the inverse has a function, that means that each y can only go to one x, which is what's happening here. So we're looking for it to pass the horizontal line test. That's what they're asking. Again, I will never ask that of you. I'll just ask the actual inverse details. So the first thing they ask is, so let G be this inverse. And then it says, find the domain and range of G. So the domain and range, first of all, f for f of x, the domain they gave us specifically was 1 to infinity. And on 1 to infinity, what we end up getting is anything, really the highest value is what we get when we plug in 1. So if you look at this, the highest value is whatever we get when we plug in 1. And the lowest value, it just goes down to 0. So the range, the lowest value is 0, and then it goes up to whatever we get when we plug in 1. So that's 1, and then e to the negative first, which is 1 over e. Again, I will never ask you for this, but if you're curious. What happens with inverses is that the domain and range just switch since all of the x values and y values are switching. So that's what they're looking for there. I would never ask you this, but just for fun. And then find g prime of 2e to the negative second. So here's what we've got figured out. So a point on f, a point on g. We know that 2e to the negative second is supposed to be an x value on g. So that means that 2e to the negative second must be a y value on f, because we know that all those points just flip-flop. So if we want to know this x value, we're going to set the function equal to this. Now that's pretty obvious. What goes in for x to get this? Well, that would be a 2. 2e to the negative 2. So this is a 2, which means the point just swaps for g. So if I want to know this derivative at this point, I find this derivative at this point and flip it, the reciprocal. So I start by finding f prime, the derivative of this function. I have the first, which is x, and then times the derivative of the second. The derivative of e to the negative x is e to the negative x times the negative 1, and then plus the second times the derivative of the first. The derivative of x is just 1. This is my derivative. Finally, I want the derivative at 2. So I plug it in, negative 2e to the negative second plus e to the negative second. And when I simplify this up, I get negative e to the negative second. So that is my derivative of f at this point. To get the derivative of g at this point, I just take the reciprocal. So g prime of 2e to the negative second is equal to the reciprocal of this. So now real quick, I have a negative exponent in the denominator, so I am just going to put it on top. So that is the derivative that I'm looking for. All right, next one we're jumping to 88 to 90. So we've got all of these values that we can pull right off the table. So g of x is equal to f of g of x. So they're asking us to take the derivative at x equals 2. So we first want the derivative of g. This is representing a chain rule because we've got a main function and a nested function. So we start, f is the main function, so we take the derivative of f and leave the nested function in place, and then we multiply by the derivative of the nested function. So that is our chain rule in the most generic possible form. And then more specifically, they want the derivative at 2, so we plug that in. Okay, so f prime and then g of 2, we pull that right off the table. G of 2 is 4, and then times g prime of 2. So let's grab those values again right off the table. F prime of 4 is a negative 2 times g prime of 2 is given as 9. So this simplifies up to a negative 18. So that's my final answer for that one. So I've got two more of basically the same type of problem. So I've got 89. Okay, so f of x this one's like a double chain rule sort of situation. So let's start by finding the derivative. So f prime of x equals, so the main function is f, so I take the derivative of f, leave my nested function in place, and then I multiply by the derivative of the nested function. So right now I'm working on finding the derivative of this, which also requires a chain rule. So I do g prime, I leave the 2x in place, and then I multiply by the derivative of 2x, which is 2. Okay, so now, once again, I am looking specifically for the derivative at 2. So every x that I have, I'm going to replace it with a 2. There we go. So f prime, g of 4 is given to us as 2. And then times g prime of 4 times 2. So let's clean this up. So these values, we're just pulling these values right off the table that you've got at the top of that page. So f prime of 2 is a negative 3. G prime of 4 is 3, and then times 2. So I actually end up with the exact same answer again. This is a negative 18. 90. Okay, so k of x equals f of x squared. So this is a slightly more tame chain rule that we've got for this one. So start with the derivative, and then I will be plugging in the 2. So my main function is f. And the thing with these generic ones that we're doing is you don't need to know what your function f is. You can get along just fine without knowing. You just need to know that you're taking f prime, you're leaving the nested function in place, and then you're multiplying by the derivative of the nested function. Okay, so now I want to know the derivative at 2. So everywhere I have an x, I plug in a 2. That's what I'm looking at. So finally I'm going to pull this value off the table. F prime of 4 is a negative 2. And then times 4, that gives me a negative 8. There we go. All right, so let me see. Where are we jumping next? Now we are jumping down to 99 through 105 odd. Okay, so 99, I have y equals the tangent of x squared. So this one I am asked to find y double prime. So the first derivative, of course, is first, and then the second derivative. So y prime, the derivative of the main function, tangent, is secant squared. I always leave my nested function in place, and then I multiply by the correction factor, which is the derivative of my nested function. So let's clean this up a little bit, just so I can take the second derivative easily. So 2x, and then remember, this secant function is being squared. That's what this 2 means right here, is that this secant function is being squared. So that is my first derivative. When I go to do the second derivative, I'm going to have to do a nice little product rule. And the product rule is actually going to require a double chain rule. So let's hold off on that for a second while I get my product rule organized. So u is just 2x. That's nice and neat. V is the secant of x squared quantity squared. Okay, u prime. The derivative of 2x, because 2x is linear, its derivative is just 2. And then v prime. Here we go. So this is your inside function. Your main function is something squared. So what happens first is the 2 comes out front. Your power technically drops down to a 1. And then you multiply by the derivative of this quantity right here. So then times the derivative of secant, because secant is the main function. The derivative of secant is secant tangent. So secant, leave the nested function. Tangent, leave the nested function. And then finally, times the derivative of the most nested function. The derivative of x squared is a 2x. Okay, so that will all be slightly cleaned up, and sorry about the space issues here. So y prime equals, finally, so we crisscross. So we do u times v prime. So let's multiply everything together here. So we've got a 2x times 2 is 4x times 2x is 8x squared. I have 2 of these, so I have secant squared of x squared, and then times the tangent of x squared. And then finally, v times u prime. So that is just plus 2 times secant squared of x squared. So very nice, neat answer there. All right, so that is number 99. Then I have 101. 101, I am doing a little bit of implicit differentiation here. I'm asked to compute the derivative with respect to x. So I start by taking the derivative of both sides with respect to x. This one's not a bad one at all. Okay, so I start piece by piece. The derivative of x cubed with respect to x is a 3x squared. As long as my variable is an x, I don't need any fancy multiples after. But then with this one, the derivative of y cubed, I'm technically doing a little bit of a chain rule. So I start with the derivative, leaving the nested function in place, but then because y is a different variable, I have to multiply by dy by dx. Equals, and then the derivative of 4 with respect to x is 0, because 4 is a constant, and constants always have 0 as a derivative. So my goal is to get this guy by itself. So I'm going to subtract this term away. And then to get the dy by dx by itself, I divide both sides by this term. Okay, so dy by dx equals, of course we can hopefully see the negative 3's are going to cancel, and I have x squared over y squared. So that would be my derivative there using implicit differentiation. 103, this one gets a little messier. I have x, y squared, and then plus 2x squared. I have a nice product rule that I've got to do here. So y prime equals, start with, so this one is u, this one is v. So u times v prime. V prime is going to be 2y, little power rule, and then dy by dx. Okay, second half of the product rule, v u prime. U prime is just 1 because x is a linear function. And then plus the derivative of 2x squared, which is 4x. So this, I guess, instead of, let's write dy by dx instead of y prime, because that's how we've got everything going here. So we want to gather up, just like we did up here. We want all the dy by dx's on one side, so this piece is going to have to move over. So we've got the dy by dx that was already there, and then I'm going to subtract this 2xy, dy by dx. That stuff's on the left now, equals, and I have a y squared plus 4x on the right. Next, I am going to factor out a dy by dx so I can try to get it by itself. Don't forget, I technically have a 1 here when I factor out that first dy by dx. Okay, lastly, to get it by itself, I'm going to divide both sides by this quantity right here. So my y squared plus 4x from the right is my numerator, and then this 1 minus 2xy is my denominator. Okay, one more in this little section here. Okay, 105, y equals sine of the quantity x plus y. So I'm taking the derivative of both sides with respect to x. Don't forget about the left-hand side. The derivative of y with respect to x, I literally write dy by dx equals, and then when I'm working on the right side, the derivative of sine is cosine. I leave my nested function in place, and then I multiply by the derivative of my nested function. So the derivative of this inside quantity right here, derivative of x is 1, and then plus the derivative of y with respect to x. So what most of us miss on something like this is that I have to distribute this cosine term. So on the left-hand side, because remember my goal is to get the dy by dx's by themselves. So first multiply the cosine term by 1, and anything times 1 is just itself. Then multiply the cosine term times dy by dx. Okay, this term right here needs to come over to the left because I'm gathering up my dy by dx's. So minus and then equals this cosine term that we're leaving on the right-hand side because it is not attached to a dy by dx. Then I'm going to factor out a dy by dx. Do not forget that, remember, I have a 1 here, just like the last one. Okay, and then finally what I'm going to do is divide both sides by this term right here. There we go. Okay, now 109. A little bit of logarithmic differentiation. And I believe that is our last one. Oops, that's a cube, so it's not the best 3. Okay, so here's how this works. Logarithmic differentiation. What I do is I take the natural log of both sides, totally legal, as long as you're doing the same thing to both sides, and then I start to simplify up the right-hand side using whatever logarithmic properties I can. So natural log of y equals, over here I start with this big quotient. So the quotient part says I can split up the numerator and then minus the natural log of the denominator. That's my first step. Next thing I'm going to do is take these powers using the third property and throw the powers out front as coefficients. Oops, 2. There we go. Okay, now that those are all cleaned up, I am going to take the derivative of everything with respect to x, left-hand side and right-hand side, every single piece. The derivative of the left-hand side with respect to x, it's the same derivative we've had every single time. Derivative of natural log of u is 1 over u, but then don't forget your u prime, and that's what this represents here. Equals, now over on the side. Start with my 3 as my constant multiple, and then like I said, derivative of natural log of u. We do 1 over whatever the u is, the nested function, and then times the derivative of the nested function. The derivative of x plus 1 is just a 1. Then minus, constant multiple rule leaves the 2 right where it is, and then times the derivative of natural log, which is 1 over whatever my nested function is, and then I multiply by the derivative of my nested function. And the derivative of 4x minus 2, since it's linear, is going to be just a 4. So let's clean up the right-hand side. So the 3, the 1, they come into the numerator. Minus, okay, so now here, the 2 can reduce this down to a 2x minus 1. And then I put 4 in the numerator. Okay, now 1 over y. Okay, last thing, because we're trying to get the dy by dx by itself, is we multiply both sides by y. Again, just like something we saw on the previous page, we're going to replace the y. So the y's have canceled on the left, but instead of y, we want to plug back in the original function. There we go. That is your final answer, and that is why logarithmic differentiation is a beautiful thing, because we don't have to worry about all the ridiculous, crazy quotient rules and chain rules that would have happened if we hadn't done this. All right, so that is our last one. Study hard and good luck.